Alright, so let's understand this problem of tree node classification. So over here we are given a table called tree which represents a hierarchical structure, right? So over here each row corresponds to a node in the tree and each row contains two columns, ID, which is the unique identifier of the node, and P underscore ID, that is the parent ID of the node, right? Now the task is to classify each node into one of the three categories. That is root, inner, or leaf, right? Now a root node is a node that does not have a parent, right? So its PID will be essentially null. A leaf node is a node that does not have any children. So no other row in the table will point to it as a parent, right? And then finally, an inner node is the node that has both a parent and at least one child, right? Now let's look at the input table. We have multiple nodes and each node may or may not have a parent. For example, node 1 has a null parent, so it is a candidate for root. Node 2 and 3 have parent 1, so they are children of node 1. And nodes 4 and 5 have parent 2, so they are children of node 2, right? Now let's look at the expected output. So we classify node 1 as the root and node 2 as inner because it has both parent and children, and nodes 3, 4 and 5 as leaf because they do not have any children, right? So the main challenge over here is how to identify whether a node has children or not, right? And once we solve that, the classification will become really straightforward. So now maybe let's build the solution step by step. So first of all, we will perform a self join over here on the tree table, and a self join, as you might know, means that we use the same table twice. So we treat one copy as A and the other copy as B, right? So table A represents the node and table B helps us find its children. And also while doing this self join, we will use a left join instead of an inner join, right? And this is important because we want to keep all the nodes, even those that do not have a children, right? And if we would have used an inner join, nodes without children would be removed completely, right? So that is the reason we will go for a left join. Now we define the join condition. So we will use a.id equals b.p underscore id, right? This means we are matching each node with rows where it appears as a parent. So effectively we are connecting each node to its children, right? Now let's observe what happens after the join. If a node has multiple children, it will appear multiple times, once for each child, right? For example, node 1 appears twice because it has 2 and 3 as the children, and node 2 also appears twice because it has children 4 and 5, right? And if a node has no children, b.id will become null because of the left join. So for example, node 3, 4 and 5 do not have a children, so their b.id values are null, right? Now we can identify the leaf nodes, right? So if the b.id is null, it means the node does not have any children, so that node is classified as a leaf. And next we can identify the root node. So if a.p underscore id is null, it means the node does not have a parent, and so that node is classified as a root, right? Now of course the remaining nodes are inner nodes, and these nodes have a parent, right? That means a.p underscore id is not null, and also have children. That means b.id is not null, right? So they are classified as inner. Now finally we use a group by, and this is required because nodes with multiple children appear multiple times after the join, right? And so grouping will help us to collapse the duplicate rows, right? And then we can also count how many children each node has, right? So now that the logic is clear, let's maybe implement this in SQL. So we select from the tree table and refer it to as A. Next we perform a left join with the same table and we match a.id with b.p underscore id to connect each node with its corresponding children. Then we group the data by a.id and a.p underscore id, and this ensures that each node appears only once, and it also allows us to count its children. Finally, we select the node ID and classify each node using a case expression. So if a.p_id is null, we mark it as the root. If count of b.id is 0, we mark it as a leaf, right? Otherwise, the node is classified as inner. Now when we execute this query, we get the final classification of all the nodes. So node 1 is root, node 2 is inner, and node 3, 4 and 5 are leaf, right? So that's how we solve the tree node classification problem using a self-join and aggregation, right? So that's it for this particular problem. I hope you understood it well, and now I will see you in the next one.